All right, happy Tuesday. I can't believe we're at week 4 already. And then I think most people got their paper topics to me, so I still need to go through those. I think I owe people a few papers. So if you, again, come across papers or want my guidance, I'm more than happy to meet with y'all or send you the paper, talk about the topics kind of more in depth. And so people were asking me questions, but the idea is you can get maybe 2 to 3 primary sources, so research paper, and then however you want to hone in on it, right? Maybe the two papers kind of complement each other and they say the same thing. Maybe you do a compare and contrast. It's really up to you. So I'm kind of leaving it open so you have fun with it. So that's the other thing, right? I want you to have fun. I want you to pick a topic that you're interested in. And you should be able to relate chemistry to any major. So I think it should be pleasant. Other questions, comments, concerns? Feel like the gas chapter went well. At least that's kind of what I'm hearing. So if you have questions on chapter 9 or anything, feel free to make an appointment with me. Happy to go over that. Um, Otherwise, just kind of use your cheat sheet for our MO theory for now. And then just keep kind of working on the 3D in your mind. All right, so now we're moving on to chapter 15 and looking at our intermolecular forces. And this is a good transition to go from gas laws to this chapter, since, again, kind of the whole problem with our ideal gas law and PV equals nRT and all this idealized equation was that we ignored, right, our intermolecular forces. So now this whole chapter is about intermolecular forces and what we ignored, essentially. And so this is nice, and now we'll start, again, getting into the structure and composition of things more to understand these intermolecular forces and how this relates to, right, like the properties of its boiling point or crystallinity, right? What is it, a solid, liquid, gas? All these sorts of things we can start to kind of guess and surmise from our intermolecular forces. And so let's just define intermolecular forces. So they are just attractive forces between molecules. And again, note the word here, inter, right? So like interstate highway. So like the I-5 or something. So something that goes between states, right? So again, this is between molecules. And so it's important to remember when we're talking about disrupting these intermolecular forces, we're not doing any bond breaking. So we're not talking about like a covalent bond or anything. We're just looking at between molecules. And so everything experiences intermolecular forces. And these are things that hold our liquids and our solids together. Again, they're what causes our gas to condense, right? Even going back to thinking about liquid nitrogen. Okay, nitrogen, that's a pretty nonpolar molecule, right? We have our same atom, so it should be fairly nonpolar, but it's still going to condense, right, from our intermolecular forces and then them coming together. And so the phases of matter, again, whether it's a solid, liquid, or gas, all that depends on the magnitude of the intermolecular forces. So we'll be able to kind of predict and rank them. And then, as we can generally see, when our thermal energy is high, matter tends to be gaseous, just kind of thinking about water in the gaseous state when it's boiling. And then when thermal energy is low, then things tend to condense. So I'll just kind of put liquid nitrogen or ice. And so we'll just look at this. So this is very vague right now, but we'll just kind of see how if we have weak intermolecular forces, then that will give us a gas. moderate a liquid, and strong a solid. But like I said, this will make more sense once we put some examples and context to it. And then just reminding us of our definitions. So definite means that it keeps our shape. So solids, right, they have a defined shape. And then indefinite means it takes a shape. And so liquids, right, they have a definite volume, and so we remember that. So the volume stays the same, but it can take a different shape. And so other things we'll look at is, so we'll look at ice, and you may know this about ice. And so what's funny about ice is the density of ice is larger than that of steam, and of course ice is slightly less so than water. And then the densities and molar volumes of ice and liquid are much closer to each other. So really we're just pointing out how far apart the particles are with steam, right? So once they get to the gaseous phase, kind of thinking back to what we said, we ignore intermolecular forces since they are further apart. And then what is odd is, of course, the density of ice is lower than the density of liquid water. So that is unusual. So water makes these nice tetrahedral-like pattern. And I didn't have a picture. Let's find it. Just so we can see why it takes up more space. So ice packs in a certain way. And so it makes an organized structure compared to more of the amorphous liquid. And so that's why it takes up more space and then is less dense. So that is unusual for ice. And then just kind of refreshing on our properties of liquids. So like we recall from first quarter, so we said liquids are closely packed, right, but they have the ability to kind of slide around and move. And so they are close packed though, so liquids are considered incompressible, right? So you can't squash them down to a smaller volume. But they do have the ability to flow and take the shape of our container. And then so just recapping, so again, liquids have a higher density than gases since our particles are close together. So just thinking about physically compressing those particles together. But they have an undefined shape from our translational freedom. So again, they can slide past one another. And then define volume, and then we can say, right, this is just kind of implying that they have our intermolecular forces to kind of hold each other. But we'll, again, kind of see this deviation in vapor pressure. So like we looked at with gases, so this is a reminder from our gas chapter. So our particles have complete freedom of motion, so they're just moving around, constantly moving. So like we said, they're moving in straight lines until they collide with a wall or one another. And then we assume, right, they don't stick. And so that's again where we have deviations from real gases and ideal gases, is how much sticking are they really doing, right? So again, in the gas phase, we're assuming they're not really doing any interacting. And so relatively speaking, right, there's a large amount of space between our gas molecules. And then gases are considered compressible with the large amount of space. Questions so far about anything? So just kind of a recap. And then, so looking at solids, so we'll kind of look at some crystalline solids and getting into a little bit of those properties. And so solids, of course, pack close together. And again, solids are incompressible, right? So they're, again, packed. And then this is a reminder. So even though we say they don't move, right, they're still kind of waggling and vibrating. So they're not completely static in nature, right? So they still have motion. So they're still stretching of bonds, right? Some sort of rotational freedom. So there's still movement going on. And then as we remember though, in our solid, right, they're not going to be flowing around. And then later, I think in other chapters, we'll cover this, or I don't remember if it's in here, but we'll look at how they can crystallize. So we've kind of like teased this of our crystalline solids. So looking at the different kind of packing structures and crystal structures there. So there's different ways to characterize exactly how they pack. And so we'll take a look at that over the course. And then we do have solids, though, that do not have nice regular packing structures. And so those are just called amorphous solids. So such as like plastic or glass, where, again, there's no true crystal. So no long range order, like I said, versus a regular ordered structure. But we'll take a look a little later as to what that means. All right, so let's look at heating curves for a second. So this chapter kind of covers a lot of different things. So heating curves now, this essentially tells us, well, how do we go from a solid to a liquid to a gas? And so right now we're looking at our heating curve of water overall. And so let's kind of look at a few different things. And so we have our heat of fusion and heat of vaporization. And so these are for our state changes. And so fusion is the amount of heat required to melt 1 mole of solid. And so again, the way this graph is set up, so we have time is on our x-axis. And so we could also kind of put energy over here because we're adding energy in with time, right? So energy is endothermic in this direction. And so now let's look at a few places. So let's look at where the heat of fusion occurs. So our state change, and this is characteristic. So once we find our plateau here, so notice, right, there's no change in temperature. So all our energy is going into our state change here. And so this first one is then corresponding right to our heat of fusion or melting. And so for every substance, you would have to look up the heat of fusion. And so here's water shown. So just over 5 kilojoules per mole. And then just keep in mind if we were going the opposite, right? So liquid to solid, that would be the change in delta heat of crystallization. So of course we just have to lose that amount. And our other big state change is of course the heat of vaporization. So now vaporization, we're going from liquid to gas, or enthalpy of vaporization. Again, it's endothermic, right, going in our positive direction, so going from liquid to gas, as shown here. And then here's the other thing to note. So you can tell by how different the length is, but our heat of fusion, and so the values are given here, but our heat of fusion, right, is much greater than our heat, or excuse me, I said that wrong. The heat of vaporization is much larger than our heat for fusion. So that makes sense, right? So gas, they're going to have more energy, right? They're moving around, they're further apart, so they have much more kinetic energy. And so we can see that, right, that we have to add a lot more energy. Again, so there it is reflected in our state change, and it is labeled on that graph. So label it if you need to. So again, we're doing a state change here, liquid to gas. All right. So now let's look at the other kind of pieces of our heating curve here. And so we've done this before. So the last legs that we need are quantifying our heat energy, right? So kind of thinking back to thermodynamics. So we did this right at the tail end of first quarter with our calorimetry cups. So at the very least, maybe you can think to that experiment. And so if you kind of think back to what we were trying to do, what the goal was, so remember we were trying to quantify the heat capacity of an object. And so we said that we can figure out how much heat was either gained or lost, right, based off of the mass. So if you recall, right, we recorded the mass of the water we use, and then we use a specific heat of water. So again, you just have to look that up for every substance. Here we're focusing on water. I'm trying to find out the specific heat is, where is it in our notes? It's further down. So this is the specific heat of water. And so the other thing, so I'll kind of note, so it depends on state of matter. And so this can be kind of a pain if you were right like off in the research world or whatever and you're trying to do a different substance. And so then you need to look up the specific heat of that substance for a solid, a liquid, and a gas, again, depending on the temperature range, right? And so other things that you would want to keep in mind are, of course, the melting and boiling point. And so let's see where this corresponds, and we'll kind of go through the math. But you can see anytime we have our change in temperature, right, that corresponds to our heat capacity. And then change in temperature, right, so we're just adding energy, so changing our temperature, so again, related to our heat capacity of our substance. And then at the very end, right, again, now we're adding heat to our gas. So we want to know our heat capacity of steam. And so that being said, on an exam, if I were to give you a substance that is not water, I'd probably give you all those points. So I would give you, like we went over, right, their melting point, the boiling point, the range of temperature we're interested in, and then the heat capacity for solid, liquid, and gas. And then let's kind of go through the math. And again, right, we keep in mind that our heat capacity could change and our units could change. So just always watch your units. So let's go through this. And so let's first look at the goal over here before we break it down. And so we want to heat 1 mole of water or ice from negative 25 degrees Celsius all the way to 125 degrees Celsius of steam. And so then that process is sketched out here. But if you were not given this explicitly on exam, I would break this up, right? So kind of keep in mind melting point, boiling point. So we have 0 degrees Celsius, we have 100. And so that's our first leg down here. So looking at this segment, right, leg 1, that's all we're doing is we're heating up our ice starting at negative 25 degrees Celsius all the way up to our state change, right, because we have to stop and then do our state change, because at this point all the energy goes into the state change. And then most of the math is, like I said, based off of the heat capacity. And so this is, again, where it could get tricky. And note that your heat capacity of ice is a little bit lower than the heat capacity of water. So 2.09 joules per gram degree Celsius. And then because our heat capacity is given in grams, right, we're going to want to convert this moles to grams. So that's why we have that conversion here. So just laying it out, so 18 times 2.09, and then times our change in temperature. So get a difference of 25 degrees Celsius. And then, so let's just punch it in so we're all on the same page. And again, right, just watch these units. They could be given in moles or something later, so I can't guarantee anything. So 18 times 2 times 25. And, oh, I guess the 2.09 really mattered. So let me try that one more time. Sorry. There we go. So 940.5, and then joules, right? Watching the units, or rounding up to 941 joules, and then probably want to convert it to kilojoules, so moving the decimal over 3 for later. Questions so far? And then, so now we do our leg number 2, right? So now it's time for the state change. And then because we're going from solid to liquid, that's where we look up our fusion. And so again, right, we have to look up our relevant heat of fusion for water. And so we get this number, so 6.02 kilojoules per mole, right? Again, we're just doing a state change, so all we need is our molar amount. So 1 mole, and we're given it in the molar amount, so 1 times 6.02, so it gives us 6.02 kilojoules there. So that's our state change. So now we're here, right? We just finished our state change. Just making sure we're all following. And so now it's time for leg 3. So now taking that liquid, right? So now it's at a liquid here. It's at 0 though. And so now we want to take that 0 degrees liquid all the way to the boiling point. And so that's what's happening with the math here. And so now this is the number you probably are familiar with if you've heard about the heat capacity of water. So relatively high heat capacity, 4.18 joules per gram degrees Celsius. Convert right back to grams based off of our heat capacity. Then we have a temperature difference of 100. And then we'll just plug it in. So our mass, so 18 times our heat capacity times 100. And so that's in joules. So about 7,520 joules there. Or converting to 7.52 kilojoules. Everybody still makes sense for the most part? And so, right, just orient yourself. Okay, now we're here. We just finished leg 3. now it's time for another state change. So heat of vaporization. So once again, right, you look up your relevant piece of data. So in this case, we need our heat of vaporization for water. So 40.7 kilojoules per mole. And then again, it's per mole, 1 mole, so 1 times 40.7. So giving us 40.7 kilojoules. Again, just kind of remark for yourself how much energy goes into that state change. Again, kind of makes sense. So now we're here, right? We have our steam. It's at 100 degrees Celsius. So we just want to take it to our last little bit of the curve. So how much energy does it take then to take that 1 mole of steam all the way to 125? And so again, we have to look up a new relevant specific heat or heat capacity. So 2.01 joules per gram degrees Celsius. So our mass back in grams to go along with that. And let's punch this in. So 18 times 2.01 and then times 25 since we're stopping at 125. And so we get 904 joules again, or 0.904 kilojoules. And then usually the question ends by then saying, like, what's the total energy of this process, right? So now we need to go back and add all our legs, right? So we went from negative 25 degrees Celsius all the way to 125. We started as ice, ended as gas. And so now let's add all our segments back up. And so I'm going to add them all up in kilojoules. So 0.941 plus 6.02 plus 7.52 plus 40 and then plus 0.904. And then, so then we should have a total energy of about 56.1 kilojoules. And so note that that's positive, right? Since we were going from ice to gas, so right, we had to put energy in. And so question is, can Q be negative, right? But if we were going the opposite way, so if we had started at 125 degrees Celsius of gas, and we said, hey, let's take it all the way down to ice, and done that same reverse process, then we would say, okay, we lost negative 56.1 kilojoules, right? So depending on which way you're going, that's what dictates the sign, right? So just to kind of recap, so when we see a positive Q, we're usually saying heat is being added. And then, right, negative Q, heat is leaving. Questions about that so far? Oh, and then other things I forgot to mention. And so let's say you were given a problem and it mentioned sublimation. And so sublimation, do you guys remember what sublimation is? Yeah.
Isn't that when something skips the liquid phase and goes straight from solid to gas?
Yep. So solid to gas. And so you may not have this value listed if you go look it up, but you can just take your heat of fusion plus your heat of vaporization, and that's the same energetically. So just note that. And so, right, CO2 is a good example of this. So you guys probably have seen dry ice, right? So that's just frozen carbon dioxide, and then it goes straight to the gas phase. So same thing, like iodine is another substance that tends to do that. And I think you guys have kind of seen that where it's those beautiful little purple crystals, and then they tend to recrystallize on the inside of the cap since it's just going from the solid to gas to back to solid phase. Yeah, or like, I don't know how freeze dry works. Do they use like CO2, I guess?
Oh, I don't know. I know that it just like instantly freezes it and then dries it.
Yeah. I'd have to look into that like more chemically because I. All right. Any other questions on this process? So it's mainly tedious, right? Like especially if you have to start all the way down here, or maybe on an exam I won't make you do all that, but you have to kind of plot what legs you are doing. All right. So let's keep going for now. And so now we want to define our intermolecular forces. And this is just reminding us, so all attractive forces between particles are electrostatic in nature. So all we're saying is, right, there has to be some sort of positive end, and it's usually attracted to a negative end. So we've seen that, right, from protons and electrons in our nucleus to cations and anions. So that's what drives all these fundamental forces. And so then, again, we'll look at these attractive forces and the strength of them. And so we can at least do kind of relative rankings, or again, kind of see why things have a lower melting point than others. And so we'll see that at room temperature, so moderate to strong attractive forces result in materials being solids or liquids. And so the stronger the attractive forces, the higher the boiling point of the liquid and the melting point of the solid will be. So that kind of makes sense. And then, like I said, we'll start characterizing them and look at their difference in strength. So weak to strong. And then the strength depends on the kinds of particles. And then, of course, the stronger the attractive forces, the more the particles resist moving. And so, again, that kind of goes back to vapor pressure, which we'll see. And again, the stronger our attractions, the more energy it takes to separate them. But again, we're not breaking bonds. So that's the part we keep emphasizing. These are not intramolecular forces, right, with an A. So that's within the molecule, but we're talking about between them. All right, so then why are molecules attracted to each other? So again, we need our opposite charges. And so looking at our polar water here, so we'll kind of get back to water and what this is. But we can start kind of sketching this out. So this is where our Lewis dot structures come into play. So we have electronegative oxygen, and then later we'll learn that this is actually special hydrogen bonding. But essentially our hydrogen here is stripped of most of its electron density, leaving it with this kind of partial positive, and our oxygens, right, carry our partial negative. And then we can see how our hydrogen orients with our other negative side. And so again, this is our intermolecular attraction between these two. And then, of course, the other concepts that we've seen still apply, like when we were talking about point charges. So I'll write the formula, right? We had this like Q1 over Q2 over the distance. And so basically, right, what that tells us, so larger charges means stronger attractions, right? Q1, Q2. And then over a longer distance is a weaker attraction, right? So there's that divided by your radius factor. So as long as they're close together And larger charges, right, that's the strongest attractive forces. All right, so let's start going through them more specifically. So we'll start with our dispersion forces. And so you may see different names for these dispersion forces. They're also called like van der Waals or also London dispersion forces. And so these van der Waals or London dispersion forces, so these are our weakest of our intermolecular forces. And so they're caused by fluctuations in our electron distribution that causes a temporary dipole. And so let's look at that. And so I like this little picture. So it's basically saying, right, if we could just take, so in this case, helium atoms, so if we could just freeze them and take a snapshot, what if it just so happens that this helium, right, has 2 electrons on the left side, so that creates our partial negative region. And then what if it's next to another one that's kind of doing the same sort of thing, and this does kind of induce a dipole as well. But then we have, right, this partial positive next to this partial negative. And so for this moment, right, they're experiencing this attractive force. We have this positive, negative. And then, of course, right, they will keep moving around the atom. So this is only an instantaneous, temporary factor. And so we see that it is weak. So it is a temporary dipole and induces a dipole. And then this also means that all molecules and atoms, right, will have this dispersion force. So that's really important. But like we're seeing, since it's just temporary, right, it's fleeting around, it is definitely the weakest force. So even though, right, every molecule has it, if there are other forces, which we'll look at, right, then this doesn't play as large of a factor. And then we can start to see the effects of different things. So anytime we're comparing molecules, we want to take into account the size, for example. And so if we just compare size versus the London dispersion forces, so let's look at what data we're given. So we're looking at just our noble gases. So that means, right, they all have our van der Waals forces, so that's it. And then the only difference is they're increasing molar mass. And so we can see how the boiling point increases, right, with the molar mass. And so that makes sense. So as our molar mass increases, right, our electron cloud increases. So we have a larger cloud that's more polarizable. And there's also just kind of more area too for attractive forces when we're comparing, right, our xenon versus helium. So that's why our xenon has our higher boiling point there. So stronger attractive forces, higher boiling point. Again, we see that just in our mass. So that's the first thing that you're going to do is, right, again, look at your mass argument and see that their masses are relatively similar or not for comparison. So other things that affect our London dispersion forces, or really any intermolecular force, is how well they pack. And so now that we are comparing pentane versus neopentane. And so let's look at the difference. So N-pentane means that we have this linear structure. So you can either look at this kind of ball and stick model, or this is kind of a good representation. And so what you're kind of imagining and what you can kind of see is you have better stacking, right, with your pentane. So now you can imagine your alkanes kind of stacking like so. So more surface area, right, for that interaction. So our intermolecular forces have, again, more surface area. versus, so look at neopentane. So neopentane refers to this structure here where you have the central carbon surrounded by your other carbons. And so this creates, right, a much more compact ball structure. And so you have a much smaller area for interaction, right? So our surface area is a lot smaller. And so you can see that in our boiling points. So again, we expect them to have a similar mass. So, right, the mass is not the confounding difference. So same formula, same mass, but the difference in boiling point is all attributed to structure. So 36 degrees Celsius versus 9.5 there. And so pentane, right, you can work with at room temperature. We're actually switching to pentane. So if you remember from last lab, we were using hexanes, and I mentioned that hexanes has that safety concern. So we are phasing out hexanes in favor of pentane, and so it's again a good choice. 36 degrees Celsius for a boiling point, so can work with, right? And obviously neopentane would not be a good alternative with a boiling point of 9.5 degrees Celsius. So that would be, right, boiling off at room temperatures. That really wouldn't work out for us. And so those are things to consider too when you're an organic chemist or any sort of chemist, right? You're trying to design something. Well, what are the physical limitations of my solvent? Kind of why, what boiling point do I need? So you can kind of use that to dial it down as well. And so with that, we can look at our boiling point of N-alkanes. And so these are all N meaning straight chain. And so we can see our mass effect, right? So as we increase our molecular weight with our increase in carbons, then that increases our boiling point. Pretty straightforward. And then just something to note is that if you were, again, kind of ranking them, doing a comparison, then any sort of branch chains would have, right, a lower boiling point. So again, that's just going to disrupt that surface area contact. And so again, just emphasizing the straight chains have that surface area, much greater surface area. All right, so now we can look at the next intermolecular force, which is our dipole-dipole interactions, or interactions between polar molecules. And so that's why it's important that you can recognize whether something is polar or nonpolar, since the whole point of a polar molecule is that it has a permanent dipole. But right, if it has a permanent dipole, that means that it always has a region of either high electron density combined with a region of lower electron density. So it always has, right, these attractive forces then between other polar molecules. And so like we're seeing here, so this is acetone that's drawn out. And again, this negative oxygen N is going to be attracted to our carbon here. I'm just redrawing that out. And so this is kind of for the future too. So later we find too that this carbon is susceptible to attack with this partial positive charge. So basically this is electrophilic, and then this oxygen is nucleophilic, so it wants a positive charge since it's negative. So it has, right, these electrons that are ready to do some action potentially. So just kind of getting you ready to see OCHEM. And then again, I like this electrostatic potential map just so we can appreciate how we have a permanent dipole there. Again, in red is showing our region of high electron density. Then blue is low or positive. And so now let's look at how powerful this permanent dipole moment is. So we're comparing formaldehyde and ethane. And so, again, the first consideration we're going to do is molar mass. So while they do have different formulas, right, their mass is pretty similar. So both pretty small molecules, around 30. But let's look at their difference in boiling point. So ethane is negative 88 versus negative 19.5. And so all that huge difference is caused right from our difference in polarity there. So pretty interesting. And then so what we find too is that our boiling points do increase with increasing dipole moments. And so if we look at our chart that's shown here, these compounds are selected since they all have relatively similar masses, right, of around 44-ish roughly. And then we can, again, appreciate, so we're starting at our nonpolar propane. And so if we were to look this up, it has a dipole moment of 0.08. So pretty much close to perfectly nonpolar. And so it has, right, our lowest boiling point, and then dimethyl ether. So now we have an oxygen in the center here. Again, a little slightly polar from that region of electron density, so 1.3. Again, we just see it slightly increasing the boiling point. Then ethylene oxide. So notice it has that epoxide shape, a little triangle, right? So that kind of forces it into a kind of more polar geometry, kind of more sticking out there. You can see from our electrostatic potential map. And then acetaldehyde, right, it's kind of on one side, so it has a slightly higher dipole moment. Then acetonitrile, we have our negative area of electron density on our nitrogen, so that makes it 4. And then again, highest boiling point just from that polarity. And so again, higher dipole moment just means more attractive forces within that molecule, or between, excuse me, two molecules. Does that make sense? Kind of track. And then, so let's finish up hydrogen bonding before our break here. And so hydrogen bonding is basically a specialized polar or dipole-dipole interaction. And so like we were looking at, when we have a very electronegative atom bonded with hydrogen, and if we look, sorry, let me pull up our periodic table, but this only occurs with our most electronegative elements. So we could either turn around or we'll look at screen. So right, it's fluorine, oxygen, or nitrogen. So maybe you want to highlight those on your periodic table. But it's only when hydrogen is bound to fluorine, oxygen, or nitrogen do we have hydrogen bonding. So again, highlight that, whatever you need to know, oxygen, nitrogen, fluorine. Very specific case. And so the significance is when we have these very electronegative atoms, like I was saying, it basically strips our hydrogen of all electron density. And so the proper term is, it's called de-shielded. So our hydrogen becomes de-shielded. And again, that makes it very polar. So our proton is basically exposed. So we can almost think of this as just a proton. And so that makes it a very strong center of positive charge. And again, it's going to be attracting the electron clouds from other neighboring molecules. And so this is like HF would be a good example. And so oops, sorry. So HF, so again, fluorine, right, extremely electronegative. So we're stripping our hydrogen of electron density there. So trying to show that. I think the electrostatic potential map kind of shows that a little better. Again, very large electron density on fluorine, leaving our hydrogen exposed. And then our interactions between our neighboring ones gives us, right, our hydrogen bond there. And so hydrogen bonds are then extremely strong intermolecular attractive forces. So stronger than dipole-dipole are dispersion. And so looking at that, so obviously we'll throw water on here. And so water has two hydrogen bonds. And so that gives it a boiling point of course, 100 degrees Celsius. And think of how small water is. It's only 18 grams per mole, so that's extremely light. But again, the power of that hydrogen bond. And then comparing other substances, so ethanol. So ethanol just has one hydrogen bond, and we see that's still significant. So it gives it a boiling point of 78 compared to dimethyl ether. So notice how they're the same formula. So right, our dimethyl ether still has an oxygen, but because it's in the middle there, and again, it's not that hydrogen bonding scenario where you have that stripped electron density, you have quite a difference in boiling points. So dimethyl ether is negative 22 degrees Celsius. So again, that really should hopefully make you appreciate the power of the hydrogen bonding there. All right. Let's stop there for a minute. So we'll take our break so we can come back at noon. All right. Do we make it back? All right, let's get back to it. So any questions kind of come up during the break or anything? And so now we're just kind of continuing with attractive forces. And I didn't bring my water cup today, but I could bring it back out. So if you remember, I have the little water cup and it has the magnets. And so the whole point being, right, this shows you how things dissolve. And again, we'll kind of talk more about this, since basically how things dissolve is we have to have stronger solute-solvent interactions, right, greater than our solute-solute. So meaning, right, our solvent, so our water has to have higher attractive forces than the ones holding together, right, our sodium chloride. And so we can see how this happens favorably. So they can go surround our anion or our cation. So of course, in our anion case, the water orients itself so that all the hydrogens are facing towards our chlorine. So again, making it soluble. And again, showing how our water is polar. And then it dissolves polar substances like ionic compounds. So again, those electrostatic forces. This goes into the like dissolves like as well. So again, we've kind of mentioned how hexane is used to clean up oil spills since it's nonpolar, so it cleans up like fats that are nonpolar, versus again, right, our very polar water is able to solubilize our ionic compound here. All right, and then this is just a recap of our strength then. So our dispersion forces being our weakest, and then increasing. And then ion dipole, this is a pretty strong interaction. It's just generally not considered part of the intermolecular forces, but do keep it in mind that, right, it's strong, and that's what leads to our solubilizing. And then other just trends to note. So what causes this outlier here? What are we seeing? Yep, so excellent. And so, right, looking at our graph, we're just comparing our group 4 and group 6 compounds, and everything mainly tracks by molar mass. But yeah, the thing that sticks out is, of course, our hydrogen bonding. And so it causes quite a disruption with our pattern there. And so here's another graph. Again, our water, HF, and ammonia all have elevated boiling points due to that hydrogen bonding. So fairly significant, that effect there. And again, right, you're just appreciating that everything is tracking by mass. With increasing mass, you have increasing boiling points, with our anomalies being our hydrogen bonding. Questions about these graphs? All right, so then a related property is in our surface tension. So let's just define our surface tension. And so surface tension is our property of liquids that results from our tendency of liquids to minimize their surface area. And so droplets, if they have strong intermolecular forces, are able to kind of form a sphere. And so I didn't bring it today, but I'll probably try to bring it for Thursday. where we can compare how many drops of water you can get on a penny versus an organic substance. That's always a fun thing. And I'm sure some of you may have done like the penny thing maybe in high school or middle school chemistry or something. Yeah. Did you do it in high school or middle school or?
I think in middle school, I don't know, it was a long time ago. I remember that though.
Okay.
You put a lot of water on top of it.
Yeah, yeah, it's impressive. Did you do that in middle school?
We did it in elementary.
Oh, in elementary? Okay. I just like to gauge, and then sometimes I like say unintentionally like insulting things. I'm like, yeah, when you did that in middle school or elementary school, and everyone's just like, we never did this. No, I'm not trying to be insulting, but yeah, if you've never like gotten bored enough to drop water on a penny, I highly recommend it. And so I'll bring in the demo, and you guys can play with it and see. And so what we're getting at, right? And so water, of course, that hydrogen bonding, all those intermolecular forces really increases that surface tension, right? So we're just saying they have really strong interaction versus, so this is benzene, wasn't really clear. So C6H6, so that's benzene, and often drawn like so. Remember, it has the alternating double bonds, delocalized pi system. So kind of thinking back to chapter 8 and 9 for that. But so delocalized pi system, but even so, right, benzene is fairly nonpolar compared to our water there. And so again, we see that in the difference of our surface tension. And so again, just re-emphasize this. So stronger the intermolecular forces, the higher the surface tension. Again, that makes sense. And then other things that can influence the surface tension is if you raise the temperature, it reduces the surface tension. And that makes sense, right? So now I would kind of think about it as we increase our temperature, right, we start to disrupt those intermolecular forces. So right now you're giving them more energy, right? So now that's going to cause them to start moving more and potentially fly away. Again, thinking of vapor pressure. Or it stretches the surface, so again, kind of weakening your surface tension. And then, so other interesting phenomenon is you can float things that are technically, right, denser than water. And so as long as there's enough surface tension, right, that can keep our paper clip afloat there. I don't know if I should. I always like show this video. I don't know if it's entertaining. If you've been in my Chem 104 class, you've seen this one. But
some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight.
all right, I mean, I find it entertaining, the video. But all we just want to show is, right, this is incredibly important to biology as well, right? So all these things that influence the habitat and why creatures can do things. So surface tension, right? Again, super important. So our poor lizard can run across the water, and sure other little animals do that as well. So beauty of surface tension there. All right, and then so with surface tension, we also have viscosity. And so viscosity is defined as the resistance of a liquid to flow. And then it's given in these units of poises or centipoises, CP here. And I mean, I don't want to get too bogged down with our units, but I just want to compare kind of, again, our relative viscosities. So we can see that water has a viscosity of 1 CP at room temperature. And then the trend we want to take away, so larger intermolecular attractions equal a larger viscosity. And so we can see that. So pentane, right, has a pretty low viscosity of 0.24, and then nonane, so our higher hydrocarbons, 0.71. And so again, that's just telling us whether it flows or not. And so the stronger the intermolecular forces, the higher the viscosity. Raising the temperature reduces the viscosity. That makes sense, right? So you've maybe heated honey or something, for instance, right, to get it to flow faster, reduce the viscosity. And then, so the other thing that's somewhat related is capillary action. Oops, sorry. Just trying to pull up something else. Where did it go? So capillary action is just defined as the ability of a liquid to flow up a thin tube. So we saw that, right, with the little TLCs, how we just had to dip it in, right, and it sucked up the liquid. So the liquid rises up the tube until the force of gravity counteracts the capillary action. And so, right, we have these two forces of your cohesion. So our cohesive forces, right, hold our liquid together. And then, of course, how it compares to the adhesive forces, so attracting the liquid to the tube. And so, kind of as a reminder to y'all as to where science has come, so it should be in our lecture notes. Oh, I don't know if these links broke. Well, I'll find some more links. Oh, sorry, failing at technology here. But Einstein actually did papers on like capillary action and cohesive forces. Okay, sorry. So this is more of a reflection paper. I don't know why the direct link to the Einstein papers, it kind of gave me a more general thing. So I'll have to dig up his capillary action work. But I mean, just appreciate that, right? Like Einstein, he's supposed to be this great genius, but even, you know, the back in the day, what I'm trying to say is like the publishing bar was pretty low, like, right, hundreds of years ago. So don't feel bad about yourselves when you're trying to figure out what the heck you can write a new thesis on. And so yeah, this is not the paper that I wanted to show, but basically, I mean, Einstein was doing work on surface tension and capillary action and like how far up liquids go. So not really fair. He had such a low bar in some ways, but that is science. Anyways, kind of fun fact. And so looking at this, of course, right, as our diameter gets smaller, then our liquid can rise higher and higher in the tube. And like I said, I'm pretty sure Einstein has a whole paper on that. I just need more time to pull that up. And so then we can explain our meniscus. And so looking at our substance here, so right, normally we look at water. And so the curving of this liquid is again due to the competition between the adhesive and cohesive forces. And so if we look at the meniscus of water, and so that's always why we say, right, measure to the bottom of the meniscus for water. And that's because the sides kind of ride up. And we see that's due to the fact that water's adhesion to the glass is stronger than its cohesion to itself, right? So it's kind of riding up on the sides of the glass here. And then meanwhile, if we compare that with mercury, so mercury is convex, right? So it's kind of bubbling more up in the glass tube because mercury's cohesion to itself is stronger than to the glass. And so this is just another generalization about metallic bonds are stronger than intermolecular attractions, but we'll kind of look at metallic bonds, I think, later in this chapter. But then to properly read, right, our mercury, we read at our top of our meniscus. And so then our other related concept is vapor pressure. So we kind of tease this, right, with the gas collecting bit, but let's go through it. And so basically, right, we're saying that there's some sort of dynamic equilibrium with the liquid, right? So we kind of mentioned this concept, and we can see it in the fact that if you leave a cup of water out, that eventually it'll evaporate. So there's some sort of amount of liquid that escapes, right? So essentially some has enough kinetic energy that it can escape, and we can draw out a chart for that. Other generalizations, of course, we can make the weaker the attractive forces between the molecules, the more molecules will be in vapor. And I don't know, I always just think of like how ethanol, I'm not a huge fan of like alcohol, and I think part of why that is like the alcohol smell always kind of hits you in the face, right? And so part of that is since it has those weaker attractive forces, so it's a little more volatile, so then you really get hit with a face full of that. The other thing I tend to think about is like ether. So if you buy a huge drum of like diethyl ether in the summertime and you pop that open, you know, you'll get hit in the face with a bunch of ether vapors. And obviously you don't want to be overwhelmed by ether vapors. Remember they used to use that back in the day as a anesthetic, right, to knock people out. So you could become potentially overwhelmed with a bunch of fumes, but generally that wouldn't happen. But again, you're just kind of hit in that face with the organic volatile smell. And so weaker attractive forces, higher vapor pressure. Again, that makes sense, right? They're not holding each other down, so they're flying up, being volatile, and ending up in your face and nose. And then, of course, the higher the vapor pressure, that's where, again, this term volatile comes into, where it's vaporous and you can smell it as a working chemist. At the same time, you tend to want solvents that do, you know, come off and you can evaporate. I often make the joke that all you do in chemistry is dissolve things and then pump off the liquid. And so that being said, you want a liquid that you can also pump off readily, as opposed to like DMSO, which you'll be there all day trying to dry that. So just lots of things to consider as a working chemist. All right, so this is a nice chart that kind of summarizes, if you remember again from lab, we had that little like table of like, here's the temperature, here's the vapor pressure of water. But this is where it's derived from, is these vapor pressure curves. So Again, I think they're mainly determined experimentally or so, but again, the whole point is once we're at 760, this is considered our normal boiling point, and then all of our substances have different temperature versus vapor pressure curves, which they follow. And then again, like we're seeing, we increase the temperature, giving our molecules more kinetic energy, so then that gives it, right, the proper escape velocity. And then again, temperature increase, which means our vapor pressure increases. And then again, our rate of growth depends on our intermolecular forces. So you would have to look up, right, your vapor pressure curve for any substance. I'm not sure if any of these are mapped mathematically. Questions so far? Don't want to zoom too fast, but all right. And then, so other diagrams that we'll see in this chapter are this other set of phase diagrams, right? So first we had our heating curves, but now our phase diagrams show something different, right? So our phase diagrams describe our different states and state changes that occur at various temperature and pressure conditions. So, okay, let's look at what that means. And so we're looking at water once again, but we could find a phase diagram for any substance. In general, you have your solid on the left side over here, and then you'll have your liquid kind of in your upper right, and then a gas on bottom. So right, you should have some defined region. And then depending on your graph, it'll have relevant points. So with this being water, that's why they've shown the freezing point, the boiling point there, so that's relevant. So generally that's going to be shown. And then we have our different curves and points here. So let's look at our different points. And so let's start with our triple point. So our triple point is here in the center. So this is just the temperature pressure condition where all three states can exist. So right, slightly lower than atmospheric pressure, and then right above 0. And then our critical point is then our farthest point on our vapor pressure curve. But let's see, I forgot to pull up our picture. Because really the whole point of the critical point is it's this kind of special state of matter, right, where it's like this phase between a gas and a liquid. I did not think about pulling up the image. I apologize. Well, I'll try to find the image that I'm thinking of, because there's a really nice picture of a fluid that's at supercritical temperature, and you can just see how the boundary disappears between the gas and the liquid, and it's just this like super highly pressurized system. But like I said, I'll find the picture a little later. So other points that we want to look at. So notice, so we have our sublimation curve. So right, okay, well sublimation, we said that was solid to gas. So that's why that's here, right, on this line, sublimation curve. Fusion curve, so remember that's our melting. And so that's why we have it here, right, solid to liquid. So kind of, again, just note these conditions where melting occurs. And then so same thing, so along this line, right now that's going to be our vaporization curve, so going from our liquid to our gas state here. see. Just making sure we hit everything. So again, make sure you can label the states of matter, solid, liquid, gas, and then critical point, triple point, and all these curves, right? So fusion, vaporization, and sublimation curve. And so again, just another phase diagram that's kind of showing you. So we have, again, 1 ATM, so it's going to show like our relevant pressure points. Again, triple point, just pointing out our different phases. All right, so let's look at our crystal structure a little. So this is now looking at kind of, this is switching now to kind of solid state structure. So again, this chapter has a lot in here. And so I don't care too much about this formula here, so we're not going to get into that. But basically, we at least just want to appreciate kind of what happens, right, when we do this X-ray diffraction. And so basically what has to happen is you start with a nice little crystal, and this crystal has to be grown kind of nicely and have what's called like a nice shape and be clear and have like a certain clarity, right? And so once you've grown your crystal, well, now you can actually X-ray it. And so that's what happens is then, right, so you literally mount it. Maybe let's get a picture. It's quite fun if you can get trained in X-ray crystallography. So now this is kind of like a specialized organometallic field. Just trying to find a nice picture of what happens. And so I like this one because this is showing how small it is. So you're just like mounting your crystal on this little point. And then I'm not really crazy. I should have searched Google. Google has better images. Actually, this is an okay one. But it's just this little machine. So you literally mount your crystal on this small point, and then you shoot it with X-rays. So this is kind of the idea of how these machines look like, and obviously radiation. And so then, right, they hit, and then they make this interference pattern. So you kind of remember from our previous chapters. But basically it makes this like kind of whole spotted image, and you can take an entire course on X-ray crystallography and like solving these structures. And so again, right, they're shooting it at these rays, and we're not going to use this formula, but you can again appreciate it. So okay, we have our formula, we shoot out our picture, so yay, pretty picture, and then basically they can solve it. So again, we don't want to get into that. That's an entire course of how to solve it. But what we want to take away is, okay, well now we can look at the actual picture and shape of these crystals. And so then we have what's called our crystal lattice. And so that's just the geometrical arrangement. And so when they're allowed to cool slowly, our particles will arrange themselves to kind of maximize our attractive forces and minimize energy. And so every substance has a certain crystal lattice packing structure. And then when you are getting your substance X-rayed and they're shooting X-rays at it, what the crystallographer Because generally nowadays people don't solve their own crystals. You have a crystallographer whose person is whole job, like they're hired by the university to shoot x-rays at your compound and then solve for your pretty picture. But they'll give you back what's called your unit cell. And so your unit cell is, so it's typically 3D, right? Since obviously, again, you're getting a 3D picture. But it is what your repeated unit cell is, right? So this unit cell is then repeated over and over and over again. And so this is kind of like your unique unit here. And so again, that's telling you what your picture looks like. And if you start anywhere within this crystal, you get that same unit cell. And again, that's the whole point of the crystal, is it's some repeated pattern. And then we'll kind of look at this. So every particle is just called a lattice point. So that's just definition. And then our lattice planes are planes connecting equivalent points. And so then we want to just look and kind of appreciate these structures. And we'll look at practice as to like the types of word problems we would do. And so we're only going to look at 3 kind of sample geometries. So let's pull up. And so we'll start with our simple cubic structure. And then atoms per unit cell. So we just have 1 in there. And so if you were to look at this, right, we have 1, 2, 3, 4, 5, 6, 7, 8 in here. But then you have like 1/8 of each little corner. So that's how we get 1 atom in there in our unit cell. And so then the idea is this is used to describe different crystals. So for example, polonium is one that does pack in this. And so this is where it says, so structure, cubic, right? So it's telling us that it packs in that cubic packing structure. Then it tells us the parameters of our cell, so how big it is. And then again, right, it's just packing in this simple cubic structure here. And then, so other relevant things that will come up later when we do word problems with this is we have our edge length. So this is, right, the edge length of our atom in terms of in terms of our structure here. And so, right, our edge length of our cube is 2 of our radius of our unit cell. And then packing efficiency just tells us how well it packs. So this only has a 52% packing efficiency. All right, so let's look at, let me try to pull up our next one. So tungsten, at least assuming I can get a nice picture. So our next one, sorry, I'm trying to pull it, there it is our bodied center cubic. And so now we have, right, an extra atom in the center, and then we still have our 8 on the end there. So now our edge length is 4r over 1/3. So let's look at our characteristic, or at least one example of a body-centered cubic. So this is tungsten. So again, that's how it packs. So you can see right now it has an extra atom compared to our polonium. I think it's kind of more evident in this space filling where it has that extra atom in the center there. So again, 2 atoms per unit cell, and then we can just appreciate how it has a higher packing efficiency of 68%. All right, so let's pull up our face-centered cubic. So I think lead, let's find lead. So face-centered cubic, so this one's a little trickier to see. So now we have, right, 4 total atoms in there. So we still have our 1/8, right? And then we have our 6 cubic faces. So we have our top and bottom. So there's 1, then 2, 3 there. So that's where we get the 4 atoms packed. And then again, our R length, so 2 times the square root of 2R for our edge length. You can appreciate the higher packing affinity. I don't think this is. Sorry. Let's try aluminum. Trying to find a face-centered. So I think this one, so aluminum, so it's calling it cubic closed pack, but I believe that's the same. So we can see, right, we have aluminum at all our faces there. So there's our space filling. So again, just showing how tightly those atoms pack in there. And so this is certainly not an exhaustive list. So if you were to go into materials chemistry, you might be more interested in this and how they pack in different ways. And so then this just kind of recaps it with the important highlights. So again, seeing how we have 1/8 of each corner in our cube, and then looking again at our edge length. So our total L of our cube is equal to 2R. And then looking at our simple cubic. So again, face-centered cubic with our 4 particles in each cell. So that will be relevant later. All right, we'll see how far we kind of get on this one. And so now we're just kind of recapping our crystalline solids, and we can talk about the different types here. And so now looking at these different solids, right, they're classified by the types of particles found and then what kind of attractive forces hold them together. So let's look at our different examples here. And so we've seen, right, our molecular solids. So we have, they're made up of molecules, and then they have low melting points, right, relatively speaking. So they put like ice as an example, but I would think of any like organic, so aspirin, caffeine. So all these still are going to have pretty low melting points. So that would probably be like 100 to 200 Celsius. So I want to say, I forget, I want to say they're like 150-ish, but somewhere in that range, right? So relatively low still. So just kind of putting things in perspective. And then comparing that to ionic solids, right? So all our salts. So he said, well, those are made out of cations and anions, and because of that, right, they had extremely high melting points. So they have table salt, but again, any ionic compound is pretty robust, right, and not going anywhere. And then, so we want to compare that to our atomic solids, right? And so when we talk about atomic solids, that means that everything is an atom. And so we'll kind of, again, look at this. And so we have our non-bonding solids. And so this would be like our noble gases, so held together by dispersion forces. And then these are going to have extremely low melting points, to say the least. So like solid xenon, for instance. So again, right, you take a noble gas and you've frozen it. So that's, again, our non-bonding atomic solid. And so now let's look at metallic bonding. So I think we had teased this like first quarter, and then I was like, okay, we'll come back to it now, though we may have to finish it for Thursday. And so part of the key of our metallic bonds is, well, it says that it's held together by metallic bonds, but that really doesn't tell us all that we need to know, so we need to come back to this. But the idea is that it's called the sea of electrons, I think we refer to it as. But we're going to look at how it's delocalized electrons. So again, we'll save this thought for a second. And then we'll compare that to like network covalent compounds. So these would be, right, structures held together by covalent bonds, extremely high melting points. So we're given quartz as one, but what would be another good one, covalent compound that we haven't talked about recently that makes a network covalent compound? With one of our most common elements. That's another good example. High melting point. Huh? What? What else has a high melting point that's a covalent? Hmm? Well, glass is like silicon dioxide, essentially. So, but what else is shiny and clear and expensive? Diamond, yeah. So it took the expensive. But yeah, diamond, that's kind of the classic one that I think of when we talk about network covalent solids. So, right, again, the diamond held together by our tetrahedral carbon, right? So again, it's all carbon, all repeating units. So again, extremely high melting points. And then you could put graphite into there as well. Of course, right, the graphite is different from diamond in that graphite is 2D. So going back to the sp2 hybridization versus, right, diamond sp3. So again, just things to think about in terms of structure and properties. But yeah, both of those are good examples of network covalent compounds. That's pretty interesting. And then, so chat put a substance of hafnium carbide, which I'm not familiar with. So I'd have to probably double check that this is considered a network covalent compound. But it does sound like it, so pretty high, obviously, boiling and melting points. So that's pretty interesting. I'm just reading about it. I'm not familiar with this. So apparently hard to synthesize, but Yeah, that's pretty interesting. And there's of course all sorts of different like carbides being developed, so lots of area for research. All right, so then this is just our chart. So kind of re-summarizing what we just did. So again, ionic crystals, all our ionic compounds, I think we have that down. Molecular crystals, like we saw, were our covalent compounds. So with CO2 and iodine, but again, any sort of organics. Network crystals, so silicon carbide. So I'm sure that hafnium carbide would be under the network crystal. And then amorphous, that was glass and plastic. So kind of the difference between your amorphous and your network crystal is also your lack of a sharp melting point. So that's what kind of defines your amorphous solid. And then our metallic crystal, we still, like I said, I'm still teasing this, but it's a good conductor of electricity. And we'll leave off on this note. Again, I'm teasing us for Thursday, so we'll look at these delocalized molecular orbitals in more detail. So yeah, let's go ahead and end there. And then on Thursday, we'll kind of look at some papers, look at this, what this really means by the metallic crystal, and what else do we have in this section. So it's kind of more hodgepodge, so we'll finish up on our colloidal mixtures and our band theory here, which goes into metallic bonding. All right, just let me know if you have questions. I'm happy to help. Oh, I do have the quiz too, if anybody needed this week's quiz, if you're not going to be here on Thursday.
I missed last week's quiz.
Okay. And then otherwise, just email me. I'm going to stop the stream.